Right, good afternoon, Year 10. What we're going to do today is we've now actually finished the topic of forces. So what I'm going to do is I'm going to quickly rattle through a few revision slides just to remind you about what we've covered in topic 5 forces. And then I'm going to set you a little task preparing for an online test, which we're going to do next week. Okay, so to begin with, I'll spend about 20 minutes doing this, and then I've got a 40-minute task which I'm going to ask you to do from your revision guide, which is quite straightforward. So, firstly, forces is mostly about vectors. Okay, now vectors, if you remember, have both magnitude, an amount, and a direction. Okay, so there must be plus or minus, forward, backwards, left, right, whatever. They need a direction. So examples of vector quantities are force, velocity, displacement, acceleration, momentum. Now, it's quite scalar quantities just have magnitude, so just an amount. So speed, distance, mass, temperature, and time are examples of that. Now, just one other thing that might trip you up. Speed is measured in meters per second, but so is velocity. They have the same unit, but one is vector and one is scalar. Okay, distance is measured in meters. Displacement is also measured in meters, but again, one is vector, one is scalar. So just be aware, although they have the same unit, they can trip you up sometimes. Okay, next. Now, there are some typical everyday values that you need to know for your exam. So there are some which you are expected to know. So pause the video, write these down, and then what is the value of these? Now remember, you're expected to know these typical values. Okay, off you go. Okay, and there they are. So walking, if you get a question about someone walking, they might only give you the distance and say work out how long it took them, but you need to know that their speed is 1.5 meters per second. Running, it's 3 meters per second. Cycling, it's 6. Car, 25. Train, 55. Plane, 250. Gravity, you might not be given gravity. You are expected to know that Earth's gravity is 9.8 Newton per kilogram. Speed of sound in air is 330 meters per second. Speed of light, 300 million meters per second, or 3 times 10 to the 8. Acceleration of falling object, 9.8. Now, most of these can be found in your revision guide on page, just quickly find it for you, 60. Okay, so page 60 in your revision guide has most of these values there. Right, other things you need to know. On Earth, gravity is 9.8, and you're expected to know this. So, for example, if we did mass times gravity, we get an object's weight, the force with which it is being pulled down. That's gravity interacting on mass. To discover something's gravitational potential energy, it's mass times gravity times height. But of course, if you multiply mass and gravity, you get weight. So actually, if you combine these two, basically their weight, their force, times their height, how high they are in meters, will give you the amount of gravitational potential energy they have. So, in an exam, a diagram like this is known as a free body diagram. You'd be expected to simplify it to this. So your skydiver, rather than drawing an actual skydiver, you would simply draw a dot. You draw the arrows, which should be proportional to the amount of force. So the length needs to be the same. So for example here, 10 newtons. This arrow is exactly the same length as also 10 newtons. Add values to show the resultant force. So in this case, our skydiver's resultant force is 0 newtons because we've got the up thrust or drag caused by the air, that would be actually plus 10, and his weight, that would be minus 10, okay, pulling him down. The size of the arrow shows the magnitude, and the head indicates the direction, so it is a vector quantity. Okay. There are many ways to work out force. Now, this unit has the most equations in it, other than possibly electricity, so there are several different ways. So, for example, work done is F times S. So, for example, just add this in. Force times distance, I know distance isn't S, gives us work done. Now, if we wanted to work out the force, we would then simply do work done divided by the distance. Remember, work done is the amount of energy transferred. another way we could do it is F equals KE. We've got force here, MFD. What could that one be referring to? Have a think. P, well, we hopefully remember what P is. P, normal P is actually pressure. So F and A, what could those be? M and A, force MA. That's probably one you are almost certainly going to come across. And then the one we did yesterday, triangle V, triangle T. So what I'd like you to do is try and remember and fill in these equation triangles with all the different ways that you can calculate force. Okay, pause the video now, off you go. Okay, so this is in page 54 in your revision guide, and you're expected to calculate a resultant force using Pythagoras. Now, we spent a bit of time on this, so just a quick reminder. If we want to know the resultant force pulling in this direction here, we need to know both the vertical component and the horizontal component of that force. So it's pulling with a force of 4 newtons in that direction and 3 in that direction. So we use Pythagoras to work out the resultant force. So you hopefully all know Pythagoras from your maths lesson. So a squared, that's a. So 4 squared is obviously 16. Plus b squared, so 3 squared is obviously 9. So 16 plus 9 equals, oops, sorry, 25. That was actually supposed to go like that. And then, of course, you need to square root it. So the square root of 25 is 5. So the resultant force going off in that direction is 5 newtons. Now, not all forces act horizontally or vertically. Some act at awkward angles. So we split them into a horizontal and vertical component. And you do this by drawing it on a scale grid. So here's an example. Let's just follow this for a moment. A toy boat crosses a stream. The motor provides 12 newtons of driving force to the north. Okay, so 12 newtons going that direction. The current causes a force of 5 newtons to the west, that direction. Find the magnitude of the resultant force. So 12 squared equals 144. Okay, add 5 squared. Well, actually, that's just from above. We worked that out, 25. 25. So a squared plus b squared equals 169. So what we do is then square root that, and we have a resultant force of 13 newtons. Okay, now you might see it on an example like this as well. There's your vertical component, there's your horizontal component. So please do have a look in page 54 to make sure this makes sense. Okay, elastic potential energy. Now, we're calculating the force, which is the spring constant times the extension. Now, it's really important that you notice something here. Here, the spring's resting position is 0.5 meters. When it's being stretched, it's 1 meter. So in this case, the extension would actually be 0.5 meters. Now, this is a bit of a tricky one because K, the spring constant, is used in this unit forces, and you're expected to remember that. However, K also crops up in the unit 1 for energy, okay, to calculate the elastic potential energy. However, they have been mean on occasion. What they might do, because this equation appears on your equation sheet all the time, it may get you to apply both equations. Even though this is topic 1 equation, because it's on the equation sheet, it does qualify that you might be able to use it in conjunction with this. So let's just say we had to calculate the elastic potential energy. Okay, so let's think what we would do. Well, let's just say we've got the force, 25 newtons, and we've got the extension, 0.5 meter. Okay, so we can work out what the spring constant is. Okay, so if we just very quickly get a calculator out. Okay, so F equals KE. So the force at the top. So we do this time we rearrange it. 25 divided by 0.5, right, equals 50. So in this case, our spring constant is 50. Right, let's just move that over there for a minute. Now, if I wanted to calculate the elastic potential energy, let's look at what I've got. Half, well, that's easy. We can put that in. So 0.5 times the spring constant, we just worked that out, 50, times the extension squared. And so in this case, the elastic potential energy would be 6.25 joules, but you can see how we've used both equations in this, okay? Just some words for you. When something is elastically deformed, it can go back to its original shape, and when it's inelastically deformed, it can't. So make sure you are using the correct vocabulary there. Right, so when you stretch an object, it is directly proportional to the force until you exceed a limit. Right, so the Hooke's law is basically saying this. As you stretch an object, the amount of force needed to stretch it is proportional to how much it will stretch, its extension. So force and extension are directly proportional until an object reaches a point, usually about here, where what will happen is it'll start to overstretch. You can see it will stretch much, much more than the force. Usually at that point it breaks. Okay, so Hooke's law states that force and extension are directly proportional until the limit of proportionality is exceeded. Okay, that's Hooke's law, and again, you're probably going to need to remember that. Okay, so fluid pressure. A fluid is anything that flows, liquid or gas. Now, pressure is exerted at a normal right angle to the surface in contact. So if you draw it in an exam, it has to be at right angles like this. Now, there are two equations which relate to pressure, and again, it might be the fact that you have to do a combination of two. This is the one you're expected to remember. It was on the equations earlier. Force, pressure, area. That has to be in your brain by next year. This one is on your equation sheet. So pressure can also be worked out by height or depth divided by, times the density of a liquid. You'll note that's an italic P, not a normal P, times gravity. So there are two ways to find pressure, and again, you may have to combine the two. So a question might be, find the force on a submarine window that's 50 centimeters squared at a depth of 200 meters, and the density of water is 997 kilograms. So they've given you the area there of the window, and they want you to find the force, but the problem is they haven't given you the pressure. The pressure we have to work out in this equation and then bump P over here. So let's see, do we have a height? Well, yes. We have a depth. Do we have a density of the water? Yes, we do, 997. Do we know gravity? Yes, we do, it's 9.8. So you can combine those, calculate the pressure, and then simply put pressure in over there, and then multiply it by the area of the window to give you your force. And it would be 977,060 newtons. For those of you that were paying attention, it's in centimeters squared, so it should be 0.5 meters, okay? That's why you get this slightly smaller number. Okay, now remember, displacement is different from distance, okay? So if, for example, we are talking about running around a track, if I say I run 100 meters like that, that's fine. If I talk about my displacement, I need to say I am 100 meters to the east. Now, say we've got a 200 meter runner, they might start there, but finish, say, up there. Okay, now in this case, our runner will run 200 meters, so around the track like this, and get to the finish point. However, the displacement is not 200 meters. The displacement is that distance. So once again, we need to know the vertical and the horizontal component of their run. And whatever that distance is, we say, I think it's about 154 meters, we'd say the displacement after running 200 meters is 154 meters to the northeast because they're northeast of their original position. Okay, so that's just really the definition of displacement. And again, please take some time to look at this. Okay, so hopefully you remember this. We looked at floating objects. When an object is in fluid, it experiences upthrust. Right, so when an object is submerged, basically, if its weight is greater than the weight of the water which it displaces, so here's the amount of water which is displaced by this apple, here's what will happen. If it is more than the weight of the water, it will sink. If it is less than the weight of water, it will float. And how much less the weight of water is will determine how much it sits on the surface. Now, pressure is greatest at the bottom because there's more weight of water pushing up. So there is a resultant force upward known as upthrust. And again, that is in your revision guide, so please take the time to look at that. Okay, 3 equations which are needed for acceleration. Okay, so acceleration can be calculated by change in velocity divided by time. That can be written out in 2 ways. Final velocity minus initial velocity over time. Change in velocity is just your final minus your initial, okay? The other way you can calculate acceleration, force, mass, acceleration, you can triangle that up. So force divided by mass will equal acceleration. You can simply rearrange this equation. And you'll see acceleration also appears here. V squared minus u squared equals 2as. Now this usually refers to dropping objects like the ruler test, okay? Now we did this one quite recently, okay? So hopefully you should be familiar with it, but the good news is you don't need to remember this one. It is on your equation sheet. However, these two, you do need to remember, okay? Right, on to the next one. Okay, so no getting around it. You need to know this method for calculating acceleration. So, check in your book, you need to describe precisely how you would do this. Basic premise of this. As you increase the mass, assuming the force remains the same, the acceleration, you can see, goes down. Okay, so it's basically as an object gets heavier, the amount it will accelerate gets less and less and less, assuming the force is the same. So, straight line means they are inversely proportional. Now, let's say this time we keep the mass the same, so the object stays exactly the same mass. If we increase the force, the acceleration will increase. So they are directly proportional. So acceleration of mass, inversely proportional. Acceleration of force, directly proportional. Okay, the next few slides are basically taken up with the stuff we've done in the last 2 lessons. So stopping distances, ruler drop, which again, I've gone through this equation with you in quite some detail, and also things like momentum and crumple zones of cars. So I'm not going to repeat myself with that. So here is your task. On page, prepare for your exam next week, on page 72 in your revision guide, there is a whole series of questions. I would like, in fact, 31 questions. Using your revision guide, I'd like to make sure that you can answer those questions. Now, this is about 20 minutes, and doing these questions will take you maybe 40 minutes, possibly up to an hour. So we might run over a little bit, but you should be able to answer these questions taken from your revision guide. Okay, so page 72 in your purple physics revision guide. Okay, just in case some of you don't have it, what I will do is once again I'll upload a photo of the questions, and then you can write the questions down and answer them in your book. If you don't have a revision guide, most of these answers should be in your exercise book though, so it should be a question of finding the answers and just checking them yourselves. Okay, right, good luck, and as always, I'll be online if you need me.